They had, and what is oscillation? Oh, and they had, and you get a lot of names. You know, many people were involved in with different oscillators. And again, it's progression, history of progression, right? How did we start doing it? You know, you start getting thermal noise, depending, provides you a little bit of fluctuation that would be fed back into a resonance circuit. And you figure the overall loop, right, feedback loop is greater than 1, your phase shift is equal to 0, so you're all locked in, nothing really major is going on here, right? And like I say, it's like noise warblings, which you're always going to get. You have devices, and you get them excited, and they are going to do things. Whether it's what you want or what you don't want, that's a moot point. But again, as you've got thermal fluctuations, you have a given circuit here, and you can expect a certain amount of noise or oscillations occurring because of the excitation, right? Then you get this guy here, probably one of the most famous one of all the oscillators. You got the line bridge oscillator. Now you've run into this name, and if I were to show out, you know, throw out a circuit at you, right, you could say, oh yeah, we got that. No. This is still widely used. You know, commercial audio generators. We essentially have 2 feedback paths as opposed to 1. You have a positive one and you have a negative one. So how would you look at that? Excuse me. So essentially, as you see here, we got the output of the lead leg going to the non-inverting, and then you got output of the voltage divider to the inverting. And that's essentially what this circuit is here. And when we're on, we have a tungsten lamp. We got an RC circuit, kind of like a tank circuit, if you will. Not totally a tank because there's no inductor in there, but that's your like resonance. So you have your negative feedback directed this way and your positive feedback directed this way. And this is an attempt to alleviate, you know, the original distortion effects that you could have going on here. And we have different styles. This was a simple one, very to the point. It did exactly its job, very easy to control. Your amount of distortion was minimal, so they tend to really have liked this circuit a lot. There's been other styles out there. They're just not very efficient, if you will. And one called the Twin T, but wasn't very popular. A phase shift style one, but again, that wasn't very popular as well. They just like to really look at these styles more for learning experiences over anything. You do have this guy, where this one did come out as a bit of popularity just because of its range. The Colpitts oscillator, you can use it from a hertz all the way up to 500 megahertz, which is quite extreme, okay? And you can easily recognize it by the capacitive voltage divider. Here, let me show you. So if we look, okay, now we notice there really is no AC occurring into this circuit, if you will, as far as an input is concerned. So we look at it as this DC approach, which allows us to do this formula right here. Instead of looking at it as a point like ecstasy and whatnot, we just look at it as straight DC analysis for this particular circuit. It's an easy one. That's why this one became so popular. It was easy to configure. Notice we have an inductor along the output right here, so we got an RLC circuit. But they have a tank circuit, and a tank circuit is basically an LC circuit, if you will. So, and if you remember the way an inductor and capacitor work, so if we look at them as being together in a parallel configuration, you're kind of going with the two phase oppositions, trying to balance each other out, if you will, to swing into the middle and provide us with a fairly stable output. This here is look better. And the AV overall of this circuit, because of the configuration involved, becomes capacitive, right? So we just literally take the value of the capacitors and doing a nice easy formula and go, oh, well, that's what our overall gain is for this circuit. And we do have to deal with a beta because we have just a simple transistor versus an op amp. So this is really a very simple circuit, but we're using capacitors in a DC nature, if you will, and deriving all of our formulas based on that. So we come up with our resonant frequency based on the tank circuit, right? It's just simple 1/2 pi square root of LC. Overall capacitance, right? You're familiar with this formula. Remember, this is a DC approach. So we can define our C as being C1, C2, right, in parallel because of the ground point right here. And then our beta, which would become in relations with the two capacitors here. And then our gain. We won't spend a lot of time on this. I just really wanted to gloss over this so you guys were familiar with it. And we have different names and as they went along. We had an Armstrong oscillator and we had a Hartley oscillator, both of which are used out there. The Armstrong actually uses a transformer, and the Hartley uses inductors, not a transformer, but actual inductors. So if we look at an Armstrong, we see they have a transformer along the output here. So we're literally driving out to the transformer. And that's why our formula becomes very interesting, if you will, where we have to look overall magnetism versus anything else, right? So our AV is L over M and our beta is M over L because we are dealing with a transistor. So we do have to take the beta into account versus using an op amp. The Hartley, if you notice, is a very similar configuration, except on the output, we don't have a transformer. We just have two conductors, if you will. Oh, what do we got here? Check. LT Spice Funder, you know, so when you get that output on LT Spice, right? So you know you can click on that. Because now you got to remember, LT Spice is looking at it as what? As a decade response. So what does that mean? So you're not looking at it totally linearly, are you? Hey, we can hold on right here. Whoa. I don't mind having a sidebar. Because actually it kind of ties in with some of this stuff too in its way. But yeah, you look at that. So you have to define your outputs if you found, right? Or you had where you have to basically define what is you know, your impedance, if you will. So I'm looking at like Z or relations to your V1 output, because when you go and run it through, all right, you're going to look at it as what? A transient response in LT Spice. And then and the way that you set that up is you're doing it as a sweep. Now, what the hell does that mean? Now, I'm sure you found out if you actually had it running. Now, do you do a continuous sweep or do you do a single sweep? Are you feeding it a pulse? Are you feeding it a sine wave? And that type of thing. And LT Spice is very tricky when it comes to that type of thing. So you have to define your input. Now, when you look at like the relationship, how does it like to look at it? And see, and this is where something they call like the superposition theorem comes in handy, because when you look at superposition theorem, what it would do is you could literally, so what you're supposed to do is you take your two voltages, if you will, and superposition, you would take as far as the circuit concerned, you would get rid of your voltage source and put a ground there instead and analyze the circuit. And then you look at the output and do the same way going back. So you get rid of these two and you kind of combine them together, and that gives you your overall. Well, LT Spice does it as well. So you have to define. Let me think now. Like if you've noticed with your V1, uh, so much fun. I'm trying to think. Hold on here. Let me back up. Yeah, so you had to define your like Ohm's law relationship, right? So you had like the V of the V1 in relationship to your I of the V1, and basically setting up Ohm's law to give you a resistance value out, right? And that would give you your Ohm's law or a linear, because your original plot was looking at it as a Bode response in a decades style graph, right? Well, you need to change that graph to a linear graph, in which case it's no longer in a decade style, log, logs of base 10, and that's how it would plot it out. But you want to change that to a linear response. So you have to define basically what your Z is, right? So your Z is equaling what in relationships to your V1 to your I to the V1. And then you got to remember, so you have your source and you have your output, and then you go through and click on your graph, and you can change that as well. If I remember this right, so you click on the graph. Let me see now. You clicked on the graph. If I did this right. Yeah. So if you clicked on the graph, you look at it on the cursor style. You could change your, when you click it, you have attached cursor, and you can change that to 1 and 2, and that would give you um, more of a linear response, if you will, as opposed to the decade response. And then, yeah, you had to set up your sweep, whether you're not, because you get a trigger thing, so you could have a single like wave go through it, right, and just give you an initial analysis, or if you wanted a continuous sweep or pulse or whatnot. But yeah, LT Spice is very nodal in nature, and it'll look at it. So you have to define what you want it to look at as far as like where your V points are and relations, and then you have to tell it basically the Ohm's law type thing, because it's wanting to look at it in the frequency domain, if that makes any sense. Because all right, oh God, I'm sidebar, and I can shut up if you want, but they had a thing called Laplace transformation, okay? And when you really look at the heart of everything, are you looking at it as a time base, or are you looking at it as a frequency base, right? And then you have to understand what's the relationship between time and frequency. So everything in the world is a time base, right? So we look at it as being that. But when we start applying the circuitry, everything that we're applying is in frequency. And then you have to understand that frequency is an inverse of time. So if you want to really truly look at what's occurring in your circuit, you have to do it as an inverse of time, which is completely opposite of the way you're used to looking at everything. And that's how you have to analyze the true response of a circuit. So then when you do the sweep through it, you're not analyzing it with a perspective to time, you're analyzing it with a perspective to frequency. So then when you want to switch and you go, okay, I want to see what this is linearly, well, you have to tell LT Spice that, because it naturally defaults to looking at it from a frequency perspective. But if you want to find out with, let's say, what your output resistance is, let's say, okay, well, that is a linear response. That is not a non-linear response. So you have to define what your linear response is with LT Spice, if that makes any sense, right? And that's essentially what the key to that circuit was that Bob gave you guys, because at the ideal output, you had to tell the graph, no, I don't want the frequency response. I want the time response. And then it changes all of it. Anyway, I don't know. But when you really get to the heart of it, I mean, that's what we're looking at when we look at AC. and why we define things as we do. Because if we take a DC approach to stuff, like in this case, right, what we're looking at is basically a straight application. We're looking at it as a time base. So we don't have to worry how this looks, okay? And that's why we can go and say, oh, well, this is this, this is this. And granted, we throw this inductor in there in the output, and that does change things, because now we're going to basically take this DC amplification effect going into the inductor side, and the inductor, of course, is going to respond as an AC point of view, if you want. But that's the whole heart of all these oscillators. That's really what's occurring, is we're doing it as a frequency. And frequencies are always, 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 always an inverse of time. And it's one of the hardest concepts to grasp, because see all this, like, okay, the clap oscillator. So how does this work? Well, we just basically apply a DC input to this thing, use the amplifier as it is here, setting up our time constant, if you will. Okay, so we have this tank circuit, L and C, right? And remember how inductors and capacitors are as far as phase opposition goes. So inductor wants to swing this way with phase, right? Remember Eli the Iceman? Well, that's a real thing. So we set them into opposition of each other to try to swing it more where we want it, right? Because if we went one way with this, we would end up with, okay, let's say we went more inductance. What does that do for us? Well, then that means our current is going to lag behind our voltage. Now, if we go with the capacitor effect, right? Capacitors don't like voltage. So, but when we apply the two together, you try to balance that out. And that's why they do, where you come up with a circuit like this, right? So we try to, what they call frequency resonance. 2 pi square root of LC. And what that does with us, it tells us, and it's based on our values. So really it depends on what we're going for as far as the frequency. And that would allow us to dictate what values we would go with on this as far as the output like this is concerned. So we would get, our desired oscillations, if you will. Now, that's not to say that this is going to be a straight sine wave output, if you will. It could vary. It could be extremely nonlinear and have all kinds of phase effects. But it's really how we set it up. And then we get something, and now these, if we really get into the heart of oscillation, you'll find a lot of the clocks out there. Initially, a lot of the PC clocks and stuff like that were set up with these guys. They actually use quartz crystals. You'll get these things out, and they come in little like can styles. They're like a strange little device, 2 lead legs coming out of it. But at the heart of it inside, there's a shaving of quartz, if you will. Because the interesting thing with crystals is they can resonate, vibrate, if you will. So if I put a crystal in an energy field, and it doesn't matter what kind of crystal it is, if I put a crystal in an energy field, it's going to start to vibrate. So, and how it vibrates depends on the nature of the crystal. Now, quartz crystals, they're real cheap, they're real easy. But if we apply a given voltage to a quartz crystal, it starts to vibrate, and it starts to vibrate at a particular frequency. So I know if I take this particular quartz crystal, plop it in, and give it an applied voltage, I'm going to get an oscillation out of it. And it's going to be dead on, and it's going to stay that way. Very simple, very cheap, very easy. I don't have to set up really much in the way of circuitry or anything like that. I just get to use this quartz crystal. Yeah, and that's a piezoelectric effect. So if you apply an energy to a crystal, it will vibrate at a given frequency. So we like to use them. Excuse me. And like all the early PCs and stuff like that, they all basically at the heart of them, they all had quartz crystal clocks. And you could buy them on the market even now, and it's like, on a given frequency, and it's a 2 lead leg to it, real easy to plop into a circuit, and you are going to get a particular frequency out of it. In fact, like my 8088 had, yeah, the 4.77 megahertz quartz crystal at the heart. And that's what this symbol right here is. That is a crystal. So we still set up the circuitry to apply us, you know, our given voltages that would go across this thing. And basically at the heart of this all, we have a quartz crystal that's going to vibrate out at a particular frequency that we desire. And we would just buy that right off the shelf and plop it right into the circuit, and it would be extremely stable. But at the heart of all these, yeah, you're still always dealing with the transistor with its strange feedbacks. You got the beta values to deal with, and so at heart, you know, they tend to be somewhat on the inefficient side. So then they came and put together this little bad boy, the 555 timer. Very easy to use. We didn't have all the inefficiencies to deal with these things. Very simple setups, the wide variety. I could do square waves. I can do sine waves with these things. I can set them up for monostable and stable operations. Can't do bistable, but yeah, if we look at the heart of a 555 timer, we basically have these two op amps, right? We have an upper trigger point and a lower trigger point. And then inside we have what they call an RS flip-flop, which is where you get your monostable operation from, is from the RS flip-flop. And we also have a transistor here. So depending on how you set this guy up is the type of clock output you can expect to see from it. But again, it's very simple, very nice, all in one chip. You can get quite a variety of configurations going on with it. If I wanted a particular monostable timer circuit out on it, really all I have to do is set up with a particular trigger point, very basic, and give it a capacitive value to provide me with my omega overall here. So I could vary the wideness of the pulse, if you will, based on what capacitive value I pick here and what resistive value I pick. And so it's a very RC oriented, and yeah, I can set it up with a 50% duty cycle where it emulates a proper square wave if I wanted to. I could make it set up for trigger pulses. But your upper trigger point has a formula, your lower trigger point has a particular formula. But I like I said, I wanted to do a lab for these guys and have you run through one. But again, like I said, I'm gonna set up 3 different labs. They're all gonna be AC oriented, all gonna be oscillator oriented, if you will. And you get to pick one of the 3. One of them will be with this guy, and it'll be like a lab final, if you will, just because I wasn't able to set up as much time with this. So yeah, you get to set up your overall time base with these things and basically set up, you know, what percent duty cycle you're going to run with these. Like I said, you could set it up totally for a 50% duty cycle, square wave output, if you will. Set it up for trigger pulses if you wanted to. It's quite a variety. I mean, we're not just stuck with doing the stable. We can also, you know, the monostable as well. So it does have, it's quite diverse, this guy is. It can do quite a few things with it. Very simple to use with the formulas. And the only thing I do have to set is what my values of R and C will be as far as my time constants are concerned, and what I'm going for overall as far as my pulses. So if I were going to go, let's say I wanted a particular time base and I could set up what my overall clock frequency would be, all I would have to do is basically come up with my formulas and start plugging away with this. And then I set up my values, and then I could just set up my values, put the circuit together, provide my input clock to basically give it a trigger point, right? And start generating clock outputs for it. Very, very simple operation. And yeah, we can do 2 different styles with this guy. This particular one is something they call pulse width modulation, PWM. You'll see this in a lot of circuitries, widely used in radio and televisions, where we do a modulation effect, and basically we can embed signals within this and do phase lock loops, which if you understood somewhat of like the feedback loops we've been looking at up to this point, phase lock loop works along a similar, oh my God, I swear to God, in that it relies on the feedback of the output to go back into the input. And what it'll do is it'll match. So if our frequency starts to deviate, it'll match with that and attempt to control it. So at any point in real time, if we start deviating on the output for whatever reason, back at the input, it'll look at it as far as a phase detector, and then it'll start to match it so we don't, okay, hold on here. When's the final? You know, fine, I'll quit talking about oscillators. No, I'm gonna post that tonight. All right. So, you know, all right, fine. When's the final? We are going to have the final tonight. I will post, it'll be a 50 question one based on the homeworks. Going through, I'll probably have more emphasis on the earlier chapters with the amplifiers and stuff. What I'm also going to do is post 3 different labs today, and you get to pick one of them as your lab final. Is how I am going to do this with this strange stay-at-home arrest stuff.
When's our last day of class?
Your last day of class officially is Wednesday.
Oh, shoot. Cool.
Is that when the final is then on Wednesday?
Oh, I swear to God. It shows how much we're listening, doesn't it? No.
So you said you're posting it today, but you haven't said when it's going to be due.
Well, now there's the fun thing. Now, officially, my books don't close until next Monday. And I don't know what everybody's schedules are. So if your schedules
Busy.
are crazy, what?
Busy. Crazy.
So if you got a crazy schedule, what I can do is I can actually have this thing be due like Sunday night if you wanted to, okay? I don't want to, because then I got a mad scramble, but it's not like I'm really doing anything much anyway, especially on Sunday. But and this is up to you guys. So this is kind of going to be my laissez-faire voting scheme, if you will. So if you guys want to, I can make this thing. Of course, it's it's going to be the easiest final in the world, right? Because it's take home. You got your books wide open and Google and everything else, So if anybody fails this final, I'm going to be very upset. And that's why I'm throwing out kind of a lab final at you. So just for something something, so you have something where you actually have to work at it a little bit, maybe per se.
Yeah.
So if I do a lab thing, you can't. I mean, yeah, you could go ahead and Google it all you want, but whether or not it's going to do the work for you, no. So, and that's why I'm really steering more towards a lab final than anything. But we can make it due Wednesday. So if
Sunday works.
Sunday work.
Yeah.
Yeah,
One in the chat for Sunday.
So what I can do is I could post these both tonight. The traditional style one with the questions, right? Multiple choice, fill in the blanks, true, false, and that crap. And then I can post, like I say, one of 3 labs, and you pick one as your lab final. I want it set up. Send me a snapshot of the darn thing working, and answer the questions for it, and that'll be your lab final. I think, I don't know, like I said, I was going through it, and it's like really the whole take-home final is kind of ridiculous because, like I say, you can literally Google the crap and everything else. And like this, if you get less than a 90 on this final, then shame on you. But I think that would be a fair thing. I don't want to make it, and it's not going to be like an insanely complicated one. It is going to be an AC approach, if you will, so that
Okay.
we do covered AC. So there might be some weird crap out there with like RC resonance, RC time constants, or that kind of thing, which you can Google if you wanted to, right? There's nothing stopping you from doing that. But as far as setting the lab up on a simulator, well, that's on you. So at this point, everybody should be able to set up, right, an op-amp feedback loop circuit with an AC input of some kind, right, with a couple of caps and inductors or resistors or whatever the heck, going into it, and getting out your particular oscillations, if you will. And I think that would be fair, and that would just show me that A, you know how to use the darn simulator after all this time, and B, that that we did kind of approach the AC things side of things with op amps and such. Because I don't feel we, yeah, I mean, I've gone through this, and I'm literally like 2 weeks. Well, you guys are 2 weeks lost. I shouldn't say me, but yeah, me, because that whole first week was the software scramble of stuff, me getting the Zoom license, getting everybody used to and getting the simulator, getting everybody licensed on the simulator and everything else. That whole first week was like, was not there. Oh, and your internet is weird. But yeah, so if you guys want, then we could set it up where it's due by 11:59 p.m. on Sunday. Okay. This way it gives you practically a whole week to do two parts, the lab and the Q&A style one. And this way, regardless of your schedules, this will give you plenty of time to do it. This way it won't mess you up with Bob's class or whatever other classes you're taking at this time and that kind of thing. I think that would be fair. And then what I'll do during this whole week as well, and this is wide open for you guys, because I have one other class, but it wouldn't really interfere overall with my time. But I can come on Zoom with you if you want, even one-on-one here. Go on Zoom. We can do every circuit. You could show me what's on your computer. If I set it up that way, I can show you what's on mine. And as far as that, so if you had any problems with the lab, you can approach me with it. I'm wide open, not 3 a.m. in the morning. I'm not gonna, there's no way in hell. But you know what I mean? Pretty much all through the day, I have no problems with that. So if you wanna, we're gonna do it at like 8 at night or whatever, that's fine. And so whatever kind of questions you might have, I'm wide open for texting if you want, all that kind of stuff. So there would be no reason why you shouldn't be able to set this up, why you shouldn't be able to contact me, and we should be able to go through this. And I think that if you go through a good AC side of looking at how an op amp responds non-linearly, right? AC, right? Non-linear. Then I feel that this would be a good cover to all this, because we've looked at everything for amplifiers at this point. We've looked at small signal amplifiers. We've seen their limitations and why they're only small signal amplifiers. We've looked at power amplifiers, and we've seen, the wide inefficiencies involved, where class B being about the only one that's pretty decent with 85%, or class A, even if you don't know the numbers, getting near about 26, 27% efficiency really blows. But, and then we looked at Darlington pairs at this point with transistors. We've looked at cascading transistors as well. We've seen their pros and cons, right? The differential amplifier, and then we looked at the cascade, and we've seen how those work, and we've seen their limitations. Then we gone in, and this sort of sets us up for the heart of the op amp, right? So you see where you have the differential in the input of the op amp with the class B being, on the output. We've seen why the op amp acts as it does, was the efficiencies involved, the ease of use for it, especially for DC applications. The thing is wonderful. But I mean, the only thing that I was not able to approach with you guys was the 555 timer. Good thing Bob was covering that, but yeah, that's the only thing we've missed out at this point. So that's why I would like to do an AC approach for a lab final. And I know it'll be difficult. That's why I want, if we give it a week, like a week project, if you will. This way you could get any formulas you need together. You talk to me. If you want, we can meet Wednesday. I'm open and do like a Q&A thing on Wednesday. If you want to do that, I can run through things on the every circuit. In fact, if you'd like, I'll plug all 3 of the circuits up and save them on my every circuit thing, and we can pull those up and even discuss them if you want. I want to make sure you get the heart of this out to you guys and everything else. I mean, when you go out there, yeah, you're not going to be electronics guys. You're not going to be setting this stuff up, but this way you understand what's at the heart of all this stuff, right? As far as like amplifiers, power amplifiers. Somebody comes up and gives you an inverter at work and says, oh, this thing ain't working. And you can kind of even understand why it may or may not work, because those are widely used out there, looking at a power supply or something like that. And it's like, oh, well, this is this. And it's like, yeah, that type of thing. But you probably won't be tearing this stuff apart down to the component level. Most times, and out there as industrial electricians, it's plug and play. You go out there, the part's blown up. You got X amount of time. They're gonna, managers are breathing down your neck. They need production going now, so you're gonna replace it. But there are some places that do have repair shops to them. A lot of places now just send it out. Rockwell Automation makes a huge amount of money doing that very thing. So generally, you just put a trouble tag on your part, state what was wrong, bag it, tag it, throw it on a shelf, and out it goes in a month or a week or whatever the time frame is, and you're done with that. But it's good to be able to understand what's at the heart of these things. And from a hobby point of view, you can definitely go through and tear stuff apart and understand why it's working the way it's working, how op amps work, that kind of thing. I don't know. But would that work for you guys? Would that be something we would want to do? Do you want to meet on Wednesday and have like a discussion, a review or whatnot?
Yeah, I think that'd be helpful.
All right. So let's do that. I will, like I said, I will post the, now you should have no problem. Like I said, I'm going to keep this like 50 questions for the the official final, right? But then, like I said, the one I want you to do some work on would be the AC lab final. I'm going to have 3 of them. I'll post them under like finals tab into the labs, and then you pick one of those 3 and go with it. And I think it'll
That
be.
sounds good to me, Tom. If you get that up tonight, I should be able to work on it tomorrow before my one class. Then we meet Wednesday. I'll know if I have any problems.
Okay. So yeah, I mean, we can do that. And that's and this way I'll make sure that, it's totally every circuit compatible. Ugh.
Yeah, I know it's been a pain in the neck, but appreciate it.
Oh yeah, well, and it was one of the reasons I didn't go with LT Spice, just because LT Spice is like so overkill in certain respects. It's an engineering tool. It really is. It's an engineering design tool. And there's a lot of other, if I'd shown you guys the one simulator I looked, it was almost like a cross between every circuit and LT Spice. So it would have been like every circuit, but a little bit more complex, I guess, if you will. But every circuit does, it does do its job. It does show us what we need to do. I actually got more out of it than I thought. I had it rammed down my throat at the beginning just because of the time frame involved. I got shot down on my on the simulator I wanted to use and that kind of thing. So it is what it is, but but this way, this way you guys get everything out of this class that you're supposed to, and then go on to your more industrial side of things with controls and stuff. But it will help you somewhat when you get into like the PLC side of things, the way you drive out with that kind of stuff, and then hopefully with your, I don't want to, what do they call that? Your finals project, your because it's not senior, it's damn it, I can't even think anymore. Where your class?
They call it the sophomore project.
Oh, all right. Yeah, because it basically any kind of a variety of, well, it doesn't even have to be automated, right?
No, it doesn't have to be automated.
It's just to be because you have to go through an initial approval too for that, I believe. Like get the project.
Yes. Yes, you have to get it approved. You have to do, it's supposed to be like a combination of a project management deal combined with using your knowledge that you've gained. So most of the projects all do some circuit level work to some degree or another, but not as intense as even we've done in these labs.
Right.
Nobody's building regulators or inverters or anything like that.
Well, I know you could use it, like for part of it, you could use your, like an Arduino or a BeagleBone or something like that and hook up like breadboards and getting responses back from things depending on what you're setting up.
Yeah, that Arduino is a real popular one. Since Bob goes through an entire class on it, almost everybody ends up using that Arduino.
I like it. Well, and they do, well, it's not just Arduino. You got, there is like the BeagleBone, which is pretty similar. And of course, then you got more complicated. You go to Raspberry Pi or something like that. All depends on how much money you want to spend and what you want to get out. But
Yeah.
but no, Arduino's nice. Got a base C. But no, let's do that. Let's do that. Yeah, and if you guys ever do run into that with the Arduino and you're having trouble with any of the C programming, let me know. I can sidebar. And I used to do oh my God, I used to do some C programming back in the day. It was always a fun little thing. One of my class projects, we actually had to write a transistor bias program, or you could input a beta and whatnot for and resistor values for your circuit. Anyway, back in the days of DOS, it was a lot more complicated then. Windows makes it much easier, but no, let's do that. I'll post that final today, and like I say, you should have no trouble with that with the Q&A. If you do, let me know. But with the lab, then like I say, I am wide open for you guys. If you have any problems with any of this crap, even with the LT Spice thing, if you need help with that, I will be more than happy to give you a hand understanding any of those weird ass concepts. But just remember, that's how LT Spice does it. It likes to do decade plots, if you will, Bode plots on the outputs, but you can change those variables to real time. And that's kind of where I was going off as frequency is versus time. Because you got to remember, all the circuits you look at are in the frequency domain, and then everything out here is in the time domain. Fun concept, but anyway, so you guys doing good? You have any questions then?
Nope, I'm good. Appreciate it, Tom.
Oh, no problem. Anything, like I say, anything you need, really, get a hold of me. I'm pretty wide open right now. This is like my only, this and one other class are my only jobs, and then, but yeah, we'll make this. I'll do Sunday 11:59 p.m. because that's one good thing about this. It leaves us more time and whatnot. But yeah, let's do that then. That's what we'll have. And otherwise, you guys have a fantastically, wonderfully cold May. I'm not going to talk about climate change or nothing like that. It doesn't exist. But it is damn cold. But yeah, stay warm, stay safe. Remember to wear your mask. I was at Casey's and like half the people don't even seem to know what masks are. Oh, I don't know.
Thanks, Tom.
Thank you, Tom.
You are welcome. You are welcome, and you are welcome. I guess so.
Thank you. See ya.